Okay, continue with the non-elementary integrals. The functions that we have been studying are called elementary functions. Integrals of functions that do not have elementary antiderivatives are called non-elementary integrals. The non-elementary integrals require infinite series or numerical methods for the evaluation. And if we use the infinite series, okay, that means, okay, this is indefinite integrals. If we mean that the numerical integrals, it means definite integrals, okay? And let me give you some examples about the non-elementary integrals. First one, which is a very popular error function, okay, ERF x error function. That means, okay, it equals to 2 over, okay, square root of pi, okay, and the integral, okay, from 0 to the x, okay, e to the minus x square del x, okay, and for this integration we know that no symbolic answer exists. And the second one, okay, and the integral sine x square del x. So it has no symbolic answer exist, okay. And the third example, integral, okay, square root of 1 plus x to the power of 4 del x. No symbolic answer. For integral e to the x over x del x, okay. And the fifth one, integral e to the power of e to the x del x. And the sixth one, integral del x over ln x. And the seven, integral ln of ln x del x. And the eight, integral sin x over x del x. And the 9, integral square root of 1 minus k square, okay, and the sine square x del x. For 0 is less than k, it is less than 1. And the infinite series it is power series, okay. Of the integrands. And now we can continue with the 6.5, which is the improper integrals. And to understand this improperty, okay, and let me continue with the example one from your book. And what it says us, find the area of the region A lying under the curve y equals 1 over x squared and above the x-axis to the right of x equals 1. Let me sketch the 1 over x squared curve. Okay, maybe this one is true. This value is 1, and this green shaded area is A, and this point is 1. Okay, X and the Y equals 1 over x square. Okay, and the A equals to integral from 1 to the infinity, okay, and the del x over x square, that means, okay. And the how can we solve this infinite endpoint of the evolution bar? And firstly take the integral, okay, and the integral from 1 to the infinity del x over x square, and after that, okay, we can change the endpoint, which is the infinity, by the any capital letter, okay, and I will get this capital letter by r, okay. So limit r approaches infinity, okay, and the integral from 1 to the r del x over x square, and it equals to limit r approaches to infinity, okay, and the minus 1 over x, evolution bar from 1 to the r, and after that a equals to, okay, limit r approaches to infinity, okay, and the minus 1 over r minus 1. So we know that when r approaches to infinity, this part, okay, will goes to 0. So it's equal to plus 1. So we can say about this area equals to 1 square unit. Okay. And continue with another example. Let's continue with the another question, okay, and find the area of the region under, okay, y equals to 1 over x above y equals to 0 and to the right of x equals to 1. Okay, these examples, okay, are same as you see, and the only change the y function. First one was 1 over x square, and the second one is 1 over x, okay, and please think about it, what can it be, okay, and maybe you can say the first one equals to 1, maybe this can be equals to 1 over 2 or the 2, okay, but the result will not be these values, okay, and the very interesting value we can evaluate, okay, and let me continue. This is the, for example, 1 over x, and this point is 1, x and y. A equals to integral, okay, from 1 to the infinity and the del x over x. So a equals to, okay, and the limit r equals to infinity, okay, and the integral from 1 to the r del x over x, so it equals to limit r equals to infinity, okay, and the ln x evolution bar from 1 to the r, so it equals to limit r equals to infinity, okay, and the ln r, okay, so we know that when r equals to infinity, ln function will go to the infinity, okay. So what can we say about it? We can say for these functions, okay, diverge, okay, to infinity. Okay, this is important. Do not confuse 1 over x function and the 1 over x square function. These are very characteristic functions about these improper integrals, okay? And let me continue. If f is continuous on a comma infinity half open interval, we define the improper integral of f over a comma infinity as a limit of proper integrals okay, that means integral from a to the infinity, okay, and the f of x del x, it equals to limit r equals to infinity, okay, and the integral from a to the r f of x del x. Similarly, if f is continuous on minus infinity comma b half open interval, then we define same proper integration by the minus infinity to the b f of x del x, it equals to limit r equals to minus infinity, the integral from r to the b, okay, f of x del x. And in either case, if the limit exists, that means is a finite number, of course. we say that the improper integral converts if the limit does not exist that means it's an infinite number. Okay, we say that the improper integral diverges. Okay, underline these two words. Okay, and if the limit is infinity or minus infinity, we say the improper integral diverges. Let me write it in the second line. Diverges to infinity. Or diverges to negative infinity. Okay, and let me give you a small theorem about it. And the integral from minus infinity to the plus infinity, okay, and the f of x del x, it equals to integral from minus infinity to 0, okay, f of x del x plus, okay, and the integral from 0 to the plus infinity f of x del x, okay, and if these parts converge, okay, and these two parts, that means both of them must converge. Okay, this equality means if and only if, okay, and if the left side of equality converge, and we can say both of them converge. If right equality, that means the two parts of integration, okay, converge to finite numbers, so we can say the left hand of the equality, which is the minus infinity to plus infinity f of x del x, converges to plus infinity, or I'm sorry, plus converges to any finite number. Okay, and let's continue with example. Which is the popular example about this. And evaluate integral minus infinity to plus infinity, okay, 1 over 1 plus x square del x, right? And when you sketch it, you will obtain like this curve, okay, and the question asks us to evaluate this green shaded area, which is A, as you see. Here is plus infinity and here is minus infinity, okay, and this function is y equals to 1 over 1 plus x squared, okay, and continue minus infinity to plus infinity 1 over 1 plus x squared, okay, and it's equal to integral from minus infinity to plus infinity. I'm sorry, here is del x, okay, and the del x over 1 plus x squared, okay, plus from 0 to plus infinity del x over 1 plus x squared. My friends, this function is an even function, so we can say it equals to 2 times, okay, limit r approach to infinity, okay, and the integral from 0 to the infinity del x over 1 plus x squared, and it equals to 2 times, okay, limit r approach to infinity, okay, and this part will be inverse tangent, okay, r, and after that it equals to 2 times pi over 2, so it equals to pi, and totally integral from minus infinity to plus infinity del x over 1 plus x squared converts to pi. Okay. Example. And the integral from 0 to the infinity, okay, and the cosine x del x, okay, and what can we say about it? And first sketch the cosine function. Okay, and you had the question in the second midterm exam. It goes like that, okay, and the question says us to get summation of this green infinite green shaded area, okay, and of course I heard lots of you said that this integration, improper integration, diverges to infinity, okay, or converges to infinity. That means that it diverges, okay. Let's continue. Integral from 0 to infinity cosine x del x, it equals to limit r approach to infinity, okay, and the integral from 0 to the r, okay, cosine x del x, so it equals to limit r approach to infinity, okay, and it will be sine r, okay, and what can we say about it? It's, we can say nothing, because of the when you say yes, sine is, for example, square root of 2, okay, we can say after the one part later, okay, and you can say square root of 2 plus, okay, square root of 4, like that, okay. I'm sorry, and that means that you cannot, okay, predict what the sine function when r approaches to infinity. So, okay, the given integral, okay, diverges, that means it does not approach any unique limit, okay. So let's continue with the improper integrals of type 2, okay. If f is continuous on the interval a comma b and is possibly unbounded near A, we define the improper integral integral from A to the B, okay, f of x del x, okay, equals to limit c approach to A from right hand side, okay, integral from C to the B, okay, f of x del x, okay. Similarly, if f is continuous on close A comma B open and is possibly unbounded near B, we define integral from A to the B f of x del x, it equals to limit c approach to B from left hand side, okay, integral from A to the C f of x del x. Okay, and these improper integrals may converge diverge to infinity, or diverge to negative infinity. Okay, and the example. Find the area of the region S lying under y equals to 1 over square root of x above the x-axis between x equals to 0 and x equals to 1. Okay. Normally, as you see, here is x equals to 1, okay, and but for this we will take the near the x equals to 0, okay, and here is 1, and this point is C, and the green shaded area is here, and the or the S, I'm sorry, this is S, okay, and that's and I'm sorry, and the S will be equal to integral from 0 to the 1, okay, and the 1 over square root of x del x. But we know that if you put the x value 0, okay, it's not definite, okay, it's indefinite. So s equals to limit c approaches to 0 from right hand side, as you see here is rc, okay, and the integral from c to the plus 1, okay, and the x to the power of minus 1 over 2 del x. So it equals to limit c approaches to 0 from right hand side 2 times x to the power of 1 over 2 from c to the 1, okay, and it equals to limit c approaches to 0 from right hand side, okay, and the 2 minus 2 times square root of c. So when c approaches to 0 from right hand side, it will be 0, so it's equal to, okay, 2 unit square. And another point, okay, and the integral from minus 1 to the plus 1, okay, and then absolute x over, okay, square root of 1 minus x, okay, del x, okay, and this is integration, okay, and the piecewise integration, think about it, and the minus 1 to the plus 1, okay, and the ln absolute x del x over square root of 1 minus x, okay, and the plus integral from 0 to the 1 over 2 ln absolute x over, okay, and the square root of 1 minus x, okay, and the plus integration from 1 over 2 to the plus 1 ln absolute x del x over square root of 1 minus x. Okay, and look at it. This point is okay, and the vertical asymptote okay, because of ln of x, interior of the ln cannot be negative value, we know that, and the plus 1 is a vertical asymptote, okay, because of the, when you put the 1 value at the denominator part, you will obtain 0, so it's a vertical asymptote, and the 0 is a singular point. Okay, so each integral on the right is improper because of singularity at one endpoint, as you see.